Hi everyone, I'm Zhan from Princeton University. This talk is on parallel repetition for all three-player games over binary alphabet, and this is a joint work with Girish, Justin Holmgren, Kunal Mittal, and Zhan. Let's start with defining the concepts in the title. What is a three-player game, or more generally, multiplayer or multi-prover games? Well, the game consists of a verifier or referee and k-provers or players. The players cannot communicate with each other and could only interact with the verifier. Initially, the verifier samples a question or input, which consists of k parts from a fixed distribution Q, and it sends to the player I the ith part of the input. Each player then, based on the part of the input it receives, generates an answer and sends it back to the verifier. The verifier decides whether the players win using a fixed predicate on the input and the collection of the outputs. Since each player only sees his own part of the input, their strategies can be seen as k functions from an input alphabet x to an output alphabet y. The game value is defined as the maximum winning probability, where the maximum is taken over their strategies and the probability is over the randomness of the question. The players could have randomness themselves, even shared randomness, but for the discussion of game value without loss of generality, we could always assume that their strategies are deterministic. Now, what is the parallel repetition? Well, in the n-fold parallel repetition, the verifier samples n questions independently and send to player I the collection of part I in each one of the n questions. Now, each player can decide its answers based on the n inputs it received altogether and send it back to the verifier. Now, the players win if they win all n copies of the game, and their strategies can be formalized as k functions, each from the direct product of n input alphabets to the direct product of n output alphabets. These strategy functions not necessarily, but could be chosen to be the direct product of the optimal strategies in each individual copy of the game. Therefore, the value of the n-fold parallel repetition of the game is always at least the original game value to the nth power. So a natural question is the reverse also true? So that the value of the parallel repetition always equals the power of the original game value. And for now gives a negative answer to this question. Then Feige actually gives a game such that when repeated twice, its value does not change. This shows that the n-fold parallel repetition value can be exponentially larger than the original value to the nth power. And there are even stronger gaps showed then by Feige and Rybisky and Raz later on. But however strong the gaps are in those examples, the parallel repetition value still remains exponentially small in n. So it leads to the famous parallel repetition conjecture by Feige and Lovász that this exponential decay is true for every game with value less than 1. This conjecture was proved for all two-player games in the seminal work of Raz and then improved by Hollenstein, and proved not very far ago by Dinner, Harsha, Venkat, and Yun for all connected games. I will define what is a connected game later on. But besides these two classes, until very recently, for every other game, it was only known that the parallel repetition value goes down to 0 when n goes to infinity by Rybisky's result. And this is proved via a black box application of density Hales-Druet theorem. And the bounds from that is pretty bad. It's basically inverse Ackermann. So naturally, we want to improve it. But before we show our results on how we improve this state of art, let's first take a quick look at the applications of parallel repetition. For two-player games, the parallel repetition conjecture, now a theorem, was famously used for gap amplifications in PCP theorems and the harness of approximation. It was also used to amplify the quantum classical separation as we have in CHSH game. The parallel repetition for a specific game called all-cycle game has a surprising application for a geometric object called foams. And the proof of the parallel repetition theorem can be used and modified to prove direct sum and direct product theorems for communication complexity. For multiplayer games, less application was known as the conjecture was not known to be true yet. But recently, Mittal and Raz showed that if we can prove a strong parallel repetition theorem for multiplayer games, we could have some good lower bounds for non-uniform Turing machines and circuits. Also, if we can prove parallel repetition theorems, we might also be able to get direct sum and direct product theorems for multi-party communication complexity. Now let's state our results in this work. We show that for every 3-player game with value less than 1, and the input and output alphabets are both binary, then its parallel repetition value goes down at least polynomially. And for every player-wise connected game, which is a proper superset of connected games, we similarly have a polynomial bound. Now, what is player-wise connected games and connected games? Well, given any game, we can define its connection graph to be a graph over all possible inputs, where if 2 inputs differs in only one coordinate, or differ for only one player, then there's an edge between them. And a game is connected if its connection graph is connected. And a game is player-wise connected if the projection of the connection graph to each player's input set is connected. We shall see an example very soon. And finally, for a specific game called the anti-correlation game, we show that its parallel repetition values goes down exponentially in N. And in this talk, I will briefly talk about the proof framework for all 3-player games with binary alphabet, and specifically the proof for the anti-correlation game. Our proof for all 3-player games with binary alphabet crucially relies on a lemma, which we call the distribution changing lemma, that allows us to focus only on uniform distributions over some support. The lemma by Feige and Verbitsky states as follows. I will not read the exact statement, but what it basically says is that if the distribution Q1 has some part being the distribution Q2, then in order to prove a parallel repetition theorem for Q1, it suffices to prove it for Q2. And now for any distribution Q1, the uniform distribution over its support is a suitable Q2. And that's why we can prove parallel repetition only for uniform distributions. And this lemma is crucial because for our goal, we know that there are 3 players with input alphabet 0 and 1. So the support is always a subset of the Boolean cube, which means that we can now do a case analysis over the support without having to worry about specific distributions. And on the Boolean cube, we have several symmetries to help simplify the classification. There's a symmetry over the 3 players, and for each player, there's also a symmetry between the 0 and 1 inputs. And it turns out there are only 6 cases for a support set on the Boolean cube. We show the inputs in the support as blue dots, and we connect the dots if they differ in only one coordinate, as in the connection graph of the game. The first 2 cases are those that I mentioned, for which an exponential decay is known. First, there are connected games where the connection graph is connected. And there are also essentially 2-player games. For example, here, the second and the third player always get the same input. So they can be seen as the same player, and then we have only 2 players. And other than these 2 known classes, the rest of the 4 classes are each represented by 1 support set under the symmetry. The first one is the 4 points that always has odd parity. This is the support for the GHD game, and the polynomial decay bound was proved for all games with this support, first by Holmgren and Raz, and then we find a simpler way to prove it. Next is the 5-point support, and it turns out to be player-wise connected. because when you project it to each player's input set, which is now just two vertices, 0 and 1, there is indeed an edge connecting them. So we have a polynomial bound that holds actually for every player-wise connected game. Then there is this 4-point support, which we call the 4-point AND support, because the third player always gets the end of the bits of the first two players. The support is just one step away from a two-player free game, and we indeed prove a polynomial bound by reduction to a two-player game. And the bound is due to a polynomial loss in the reduction. And finally, we have this 3-point support that has Hamming weight 1. We didn't prove a bound for this case in this work, but we did manage to complete it in the follow-up work, and I will mention it again at the end of the talk. However, what we did prove for this support is an exponential bound for a specific game, the anti-correlation game. So let's define it. The input, as we said, for the 3 players is a uniform distribution such that 2 players gets 0 and 1 player gets 1. Each player has to output 1 bit, and they win if the 2 players who gets 0 output different bits. This game clearly having a value of 2/3 is very interesting because its value does not change if you repeat it in parallel for 3 times, as noted by Feige. What's more interesting is that its value in the non-signaling model does not change at all under n-fold parallel repetition for any n. This is an example that shows that there is no parallel repetition theorem in the non-signaling setting, and it was proved by Holmgren and Zhan. And this game is interesting for us because we did another case analysis and found out that every game with this support and also has binary output alphabet is one of the following cases. It's either trivial, or could be reduced to a 2-player game, or is equivalent under symmetry to the anti-correlation game. Therefore, after we show the exponential decay for anti-correlation game, the exponential bound actually holds for every game with the support and binary output. And combined with the case analysis that we did earlier, it implies a polynomial bound for every 3-player game with both binary inputs and binary outputs. So let's dig in a little to the proof of the anti-correlation game. We know that our proof is interesting in its own right because most of the previous bounds on parallel repetition uses a framework of embedding, whose goal is to basically find an embedding or many embeddings of the original game in the parallel repetition game. But our proof is completely different from this. Our starting point is a dream scenario called global strategy. So if the player strategies are globally usable, that is, if the strategies are actually constant functions, then in each coordinate, the inputs has at most 2/3 probability to suit their strategies. So the winning probability is at most 2/3 to the power of n. But of course, this is too good to be true because the players has no reason to stick to a global strategy. The good news is we can have some relaxations on the global strategy. So let's assume that the players use some optimal strategies that achieves the optimal value of rho. The first relaxation is that each player can have a bunch of global strategies instead of just one global strategy, as long as there is a tuple of global strategies for each player that accounts for a small portion, say polynomial in rho of the winning probability, we can still show that rho is exponentially small. And secondly, the global strategy does not have to be extremely strict. Each player on each input can deviate from the global strategy on a few coordinates, say epsilon n coordinates, then excluding all the coordinates that some player deviates, we still have linear in coordinates to bound their winning probability. And similarly, we only need to specify a global strategy on a fixed linear number of coordinates. The rest of the coordinates can be fixed to our will. So if we can extract such relaxed global strategies from their optimal strategies, we're still good. So now it sounds achievable. How do we actually do that? Now let's consider the inputs as a bipartite graph. On one side is all possible n-bit input x to the first player, and on the other side is all possible n-bit input y to the second player. A valid input is an edge between x and y, because z, the input to the third player, can be determined from x and y. And we also color the edges that represents the input where the player's strategy win as red edges. We are now interested in this structure where two inputs x and x prime has a common neighbor y that wins with both x and x prime. We want to say that this structure has high density in the graph. So we introduce a sampling process that first samples y according to the correct distribution from the repeated gain, where each coordinate has 2/3 probability to be 0 and 1/3 probability to be 1. Then we independently sample x and x prime uniformly from y's neighbors. Now the fact that the red edges has density rho in the graph means that the probability that both edges that we sampled are red is at least rho squared by Jensen's inequality. That means a polynomial in rho fraction of the pairs x and for a polynomial in rho fraction of the pairs x and x prime drawn from the distribution from that sampling process, there are a polynomial in rho fraction of y that wins with both. And what does it mean when y wins with both x and x prime? It means that the first player's answer on x and x prime are consistent on every coordinate where y is 0. Because as you've seen from this example here, if both x and x prime are 0 there, they need to be simultaneously different from the bits of y. So they must be the same. And if one of them, one of x and x prime is 1 there, then the output doesn't really matter, and we can change it to be the same. So we also know that a large fraction, polynomial in rho fraction of different y's wins with both x and x prime. So the number of inconsistent coordinates is actually in the answers to x and x prime is actually bounded by logarithmic of 1 over rho, which is epsilon n if we choose rho to be large enough, but still remains to be exponentially small. Okay, so now these consistent coordinates are exactly those where the first player choose to deviate on. If we pick a typical x prime and let the answer on x prime to be a global strategy. This global strategy accounts for a polynomial in rho winning probability because such fraction of x paired with x prime is good. But is it? We show this question mark because there is actually one problem with this claim, that it works under the distribution given x prime. Because x and x prime are not independent from our sampling process, the distribution becomes different after conditioning on x prime. The good thing is that the distribution conditioning on x prime is still independent across the coordinates. And if we look only at the coordinates where x prime is 0, which has like 2/3 of n coordinates for a typical x prime, the distribution there on x and y is just a little biased. It has the distribution 1/4, 1/4, and 1/2 instead of the uniform distribution. So our solution to this problem is to call the distribution changing lemma again. Because we can prove the claim for the winning probability of a global strategy under this bias distribution, the lemma just translates it to a claim under the uniform distribution, but with a smaller n. But this smaller n is smaller just by a constant factor, so we're fine. Or equivalently, what we can do is to fix the distribution. What we can do to fix this distribution is by a random restriction, and it only fixes a linear number of coordinates, and we still have a linear number of coordinates to spare. And now we find a global strategy for the first player. We can do the same for the second player and the third player, and that completes the proof. Okay, so now let's briefly discuss some follow-up works and the future works. The obvious question you ask is that, can we extend these completely new methods to other games? And we kind of did. In a follow-up work, we use similar ideas to prove a polynomial bound for all games with this 3-point support, and thus completes the case analysis. And we can claim the polynomial bound holds for every 3-player game with binary input without limiting the output alphabet. And that proof also uses many new ideas and techniques, and most notably, it was proved by proving the bound for the hardest game with the support. Hardest in the sense that every game with the support can be reduced to it. So I'm curious that, do we have a hardest family of games that can cover all games? And also they have some simple form to analyze. Because we do have a hardest game for every support set and output alphabet via some syntactic construction, but it's too unnatural and hard to analyze. And finally, now that we extend the border of the games which we have bounds for, and specifically the anti-correlation game with the exponential bound, do we have some interesting applications from those bounds? And that's the end of my talk. Thank you.